class we learned about fork, creating a process, right? And fork's kind of an odd bird because what fork does is fork duplicates your address space. Has the operating system create a whole new process for you. That process is a duplicate of your process, which means now we have two running entities and both of them will return from fork, right? Because both of their memories are set up the same way, which means they have the same code, globals, heap, and stack. The stack is why they both return from the fork call. The parent, it's kind of normal, it returns to the fork call. The child, it's weird, it just starts in the middle of its life, right? And then it returns from a fork call, perhaps in a whole sequence of procedure calls, but since the stack was copied, everything looks the same. The only difference is that fork returns the process ID of the child returns process ID of 0. That's how you know one of them was the parent. That's how you differentiate the two processes, because they're both running the same code, so you're running the same program. Okay, wait is the next system call. Okay, now there are a bunch of waits here. You're not calling these. These are for weak people. You're going to call wait, the real wait, because that's how you write the best programs. These make you write bad programs. Okay, what wait does is, we'll talk about what you pass it. Well, you pass it a pointer to an integer, which it's going to fill in. Okay? And now what wait does is that if you have a child, if you forked a child, you're the parent, wait's going to wait for your first child to die, not the first child that you gave birth to, right? If you have multiple children, it's just going to return the first one to exit. Okay? It's going to return the process ID of the child that is exited. And then it's also going to fill in this integer, stat loc. It's going to fill that in with some extra information about how the child died. Okay? So if you don't have any children, wait just returns, which I'm not sure if I like, to be honest with you. But it'll return with the return. Well, we can check out what the return value is. Right here, let's write some code. Here, standard out of H. Standard lib, hopefully unit stood, and that's all we need. Int main. Let's say pid t pid int status pid equals wait status printf and pid return 0. Let's go ahead and get ourselves a second window. A little smaller, make that a little smaller. Sure. Okay, so GC, have we written it? There we go. Okay, we don't have any children. Wait returns instantly with a process ID of -1. Okay, are we going to use that fact? I don't think so. Actually, I don't think that you're going to use that fact in any of your programs. Okay. Now instead, if you call fork, so if fork does not equal 0, okay, and that means I'm the parent, I have a child, now I'm going to wait for my child to die. And then if I'm the child, what should I do? Let me sleep for a second. I'll live for a second before I die. So sleep 1, return 0, okay, and I'm done. Okay, so as advertised, right, I called fork. I can even say what I got right here, fork. Oh, I'd have to store it. I won't bother. Well, there we go. Child. So we can not lie, and then we'll do that, and we'll solve it. CH. All right. Okay, so very exciting. Now, there in the status is a bunch of stuff, okay? And in that bunch of stuff, it tells you a couple things. It tells you how did the kid die, okay? And then if the kid passed a return value, what was that return value? So I'm not going to do this one live because I never memorize this stuff. But we can look at fork weight. I'll just copy it. Weight 1.c to junk.c. Okay. So there in sysweight.h, there are a bunch of macros, and the macros will tell you some things. So these are all things about the status of it. So exited means, did it exit normally? Did it exit by calling the exit system call, or did it return from main? Right, those are two ways. If that happens, this will be true. If that's true, then exit status, that's going to be what this exit call was made with, right? So when the child says exit 0, you always wonder, why do I have to do this? Well, that's because the parent will read that. That's how the child can communicate an exit code back to the parent, right? So if we run this, so what's the child going to do? Yeah, the child's just going to call. So let's walk through it. I call fork. If I'm the parent, I call wait. So now the parent's going to wait for the child to die. Child's going to print out its PID, going to call exit 0. Okay. And yeah, as the comment says, if I had said return 0, it would have done the same thing. Okay. And so now, when I call it, right, there's the child, we got the proper process ID, and then here's that status integer, but as you can see, in the status, this is 1 because it exited normally. And then if in my child, I say exit 1 instead of exit 0, and I run it, now you'll notice, that's interesting, what that is. Right, now you'll see that the exit status is 1 instead of 0. Okay. Now by convention, we return 0 when our program exits normally and 1 when it exits abnormally, and then that's nice because then programs like make can exit compiling early, right when the compiler fails, or when you run a shell script, you can write the shell script and see whether your subcommand failed or not. I don't ever use any other exit status codes. I don't even know what they go to. Like, I'm guessing it's a char or a short. You could probably read it on a man page someplace. Okay. Now, if my process didn't exit early and it died by other means, like, so what is that? Well, one way I could do that is I could have my child here. I'll have my child say sleep 10, and then I'll kill it with a signal. All right, so here's GCC. And let me get another shell window for this one. Okay, we'll run it. I'll do a PSX, which shows me, I have 2 A.outs, but I bet that's the child. So if I say kill that, I just killed the child. Okay, and so now you'll see the signal thing is now saying it's true, and it's saying signal number 15. Right? There are a bunch of different signal numbers that you can use. So here, if we run this again, well, actually here, if I run this again, I could say, I'm not sure I'm going to get it in my 10 seconds. If I say kill-9, nope, I didn't get it in time. Let's have this sleep longer because I'm slow. Really? Okay, here. There, even I can make it in that. All right, so now I'll do a PSX and I can say kill 96517. Okay, so now you'll see that it got the signal on, right? A segmentation violation is in fact just a signal, okay, but it's a signal sent from the operating system to you. So if I have my child die on a segmentation violation, I'll be able to see it, all right? So here, char star S equals char star null, J equals star S, right? That should get me a seg fault. Right, you'll see when I run it. Yeah, signal, and seg fault signal is number 11. If you do kill-L, it tells you what your signals are. Okay, so we'll talk about sig alarm quite a bit. So there are a couple signals that you use. Sig terms one, sig quit's another one that are sometimes nice to use. We'll talk about sig pipe. Sig 9, sig kill is supposedly the signal that you can't catch. because your program can catch signals, but in theory, you can't catch signal number 9. I say in theory because there have been programs that you can't kill ever. All right. Just double check, make sure I've got all my weight stuff. Oh, I will do it. If I call fork multiple times, okay, so here, let me do this how I do it in the lecture notes. So here, int seconds 5. And now I'll do seconds. We'll talk about why I have to do it this way. Second 0 equals, let's go with drand 48 times 10. All right, do we all know what drand 48 does? Returns a random double between 0 and 1. It's a horrible random number generator. You should never use it, but the nice thing is it's there. It always exists, so if I'm writing quick and dirty programs, I'll do that. And now, here, for I equals 0, I is less than 5. I guess I could have done that in this loop. Printf seconds d equals d. So I seconds I. And now what I'm going to do is I'm going to do the following. I'll start with j equals 0. No, I'll go for j equals 0, j is less than 5, j plus plus. And there I'm going to say I equals fork. Okay, so now, again, fork copies the address space. So the first child here is j is going to be 0. The second child, j will be 1. Third child, j will be 2, etc. So what I'll do here is I'll say if I equals 0, meaning it's the child, I'm going to sleep for seconds j. And then I'm going to exit. Okay, so now I don't have to do anything because my parent's going to get control. And now I'll have my parent call wait 5 times. Now that I'm done, now I'm going to have my parent call wait. Okay, so do I have I'll just set it to I. So I equals wait, status, printf, child, d, done. And that'll be I. All right, and so while I'm here, why don't I also, here I'll print out, printf, child I is that j. I. There we go. Okay, so setting up an array of times to sleep, I'm going to fork off 5 children. Each child will have a different value of j. Okay, because I just get the address space when I call for it. Child is going to sleep for a certain amount of time, then die. By the time any child is running, unless the sleep times are 0, so here, let me make the sleep time non-zero. Okay. By the time the parent hits this loop, all of its children are sleeping. So now the parent's going to call wait 5 times. That's not going to compile, is it? Going to call wait 5 times and print it out. Why didn't you tell me? You saw it, didn't you? How many people saw it? Yeah, 1, 2, 3. Not feeling the love. Okay. So we should definitely get child, yep, here we go. Bless you. Right? And so we'll definitely get, so child 1, which was 9661112, that should be the last one. Yep. Okay? And the first one's going to be one of these 3, right? These are all at the same time. Right? And so who came first? Child 2 came first, then child 0, then child 4, and then child 5. Yep. And then the last one. I just do this to show you it doesn't matter when you create the children, it's when they die that this matters. Okay, now let us do something else. All right, we're going to do something a little different now. Let's kill it. We're going to fork a child. So I equals fork. Then what we're going to do is the child's just going to die. So if I equals 0, exit 0. Okay, so child is dead instantly on this. And then what I'm going to do is I'm going to have the parent call sleep. So parent will call sleep, let's say 2 for 2 seconds. So that by the time the parent wakes up from that sleep call, the child is good and dead. Okay. Question is well, a couple things all right, is wait going to work now? Kid's already dead. I would hope it does. But the other thing I'm going to do is I'm going to do a PSX here. I'm going to do system PSX. Hope that works. And then I will say I equals wait. Let's print. No, that's okay. We'll see it. I'll say I equals wait status, and then I'm done. Return. Okay, run this, child dies. Okay, we've done the PSX call, we've done the wait call, seems like it's returned. I probably should have printed out the return value. Let me print out the return value. Wait, returned. All right, run it again. Same thing happened. Okay. Why do I do the PSX? I wanted you to see this. Okay. The child is dead. Okay. However, when I call PS, the child's entry is still there in the listing. And it has a status called Z, and it's in parentheses. Okay. What's going on is this is called a zombie process. If you die and your parents haven't died and they haven't waited for you, okay, then you are a zombie process. You don't consume any CPU resources, but you do consume resources in the process table. And I bring this up because if you fork off a ton of processes and you don't call wait, you're going to get this accumulation of zombie processes. And you do a PS and you'll see 100 zombie processes. And if you keep going, you'll run out of process IDs, right? Because they'll all be consumed by zombie processes. And the only thing the operating system is doing is the operating system is just holding this around so that when you call wait, you'll get back the information about how the kid died, and then it cleans up the zombie process. So it's a good thing to know. Now, recall what an orphan process is. Right? An orphan is a child with no parent. So what that would mean is if I'm an orphan process, it's kind of the opposite way around, right? If I doesn't equal 0 exit, now parents around, right? I'm now a zombie. Well, let's just do the PSX. I won't call wait, okay? But the child will die. Whoop. Okay, you know I get the prompt back because the parent waits on the prompt. Okay? But there it is, right? It's running. If I call get ppid, it'll return to me a value of 1. Because remember, orphans get inherited by the initial process on your system. Okay? Here. Get ppid. There's my parent. My parent is now 1. So this initial process, one of its job is actually to clean up all the orphans. So whenever your orphan process dies, this one automatically calls wait for it, cleans it up. So your orphans can never become zombies. If you're an orphan, the only way you can become a zombie is if you die, your parent's alive, and your parent's not waiting for you. Well, if you're an orphan, your parent's in it, and it's going to wait for you and clean you up. Okay? All just nomenclature you should know. Okay. I think that's it for wait. It seems like a lot of mileage out of wait. All right. Now, I will say, you're going to write a shell. Okay? Your shell is going to have to process lists of commands that are connected together with pipes. Okay? Like when you do cat something and pipe that to grep and pipe that to sed, pipe that to head, right? You're going to have to set all of that up, which means you're going to call you're going to call fork a bunch of times, and then you're going to have to call wait a bunch of times. And what happens is you're not going to know which process comes back from wait. So you're going to have to keep track of your processes so that you know when a process comes back from wait what you should do with it. Now you're gonna want to be lazy. I can just tell you because I've taught this 8,000 times. Right? Is that you're gonna type man wait and you're gonna see, ooh, there's wait PID. Wait PID says please just wait for this child to die. That's weak. Keep track of your own damn children. Okay? No babysitters in the operating system. All right, so you're calling wait. You're not calling wait PID. God forbid you're not calling wait 3 or wait 4. Asynchronous waits. I mean, those shouldn't even exist. All right, a polling wait. It's horrible. So no, none of those. You're just going to call wait. Okay. Exec VE. Let me follow my notes on this one. There we go, 360 lecture. Oh, fork bombs. There we go. Okay, I think I've gone through everything here. Yes, I have. Okay. Exec VE is confusing. Okay. Now with exec VE, what this is doing is you are going, first off, let's get NFP out of the way. NFP are your environment variables. If you say print end in your shell, you'll get these environment variables. Some of them are useful, like home. Right? Home is always your home directory. User is you, right? Which are nice things to have. But you can set them. So in your shell scripts, I've set a whole bunch of these because they're useful for me. But if you call, when you have your main, you can give it a third argument called envp. And that'll actually be a listing of these. It's just these strings. It's a char double star, null terminated, where each one is one of these. Okay. So it's a way. So this is how your environment variables get propagated from one program to the next. Okay. It's not that important for you to know, but it is so that you can understand exec VE. Okay. So with exec VE, you give it an executable file. Okay. So what's an executable file? Like your a.out. Okay? You're going to give it an argv array. So this is like the array that you get with argv. Only you'll notice there's no argc. And the reason is because you're going to null terminate that argv array. So the last element is going to be null, and then argc gets calculated for you by exec VE. And then if you're using an environment, you can pass the environment. Now what exec VE does is the following. If all the arguments check out with the operating system, then it's going to overwrite your process. Your memory, it's going to overwrite it. And it's going to overwrite it so that the code's coming from here, right, the executable file, and the globals will be set up from the executable file. You'll have an empty heap, and you'll have a stack, and your stack will be set up so that you're running main with argc and argv and envp as the arguments. Okay? Now, when that happens, your memory's gone, right? You've given the operating system this call. The operating system has trashed your memory. This never returns. It has no place to return to. Your stack is gone. Okay? So when you make this call, it does not return if it's successful. If it's unsuccessful, it will return, and you'll have an error code. Okay? So some people say the vernacular is that fork returns twice and exec doesn't return at all. Right? So fork returns twice, right? You get two processes, each process returns once. With exec VE, when you call it, it never returns. So what happens when it's done? Well, the process gets cleaned up by the operating system. Okay. So the path that a shell takes when you want to execute a command in the shell is going to call fork, create a child. Okay? The child is going to call exec VE, turn into another process, but it still has the same process ID. So the parent is calling wait. The parent doesn't care if it called exec VE or not. It's just waiting on that process. When that process dies, Okay? Then the parent's wait call can come back. So let's first just write an exec VE that does something. Okay? So what we'll do is, oh, here we go. We got this one here. Here's what we'll do, is we will, well, first off, let's get ourselves a file. Or maybe I've got one, f1.txt. Well, that's boring. Here, random names 10 into temp.txt. All right, I got 10 random names there. Now, and now what I'm going to do here is I'll say char argv 4. That's not good. Char star argv4. Okay, so I have an array of 4 char stars. And now what I'm going to say is I'll say argv0 equals cat, and argv1 equal cat v. Argv1 equals which cat, right? Which doesn't work in all of them, in all Unixes, which is unfortunate, but which will tell me where cat is. I think I've told you this before. You have a path environment variable, and that tells this is where when you say something like cat to your shell, this is where it finds the program. So what it's saying, what my which program is saying, oh, it's really there in bin cat, right? So if I do ls-l/bin/cat, okay, there it is.
You wrote erg C instead of erg V.
Oh, thank you. Team plank. All right, so this is going to be bin cat. No, that's not going to be that. That's going to be cat. argv1, this will just be 3. argv1 will be temp.txt, and then argv2 is going to be null. And then I'm going to call exec VE with, do I need an env pointer? Let me get, just be safe, I'll get myself an env pointer. I'll make it 1, and I'm just going to set it to null. I'm going to clear out my env. So env0 equals null. And now I'll call exec VE, and I'll call it on bin cat, argv env. And now here printf did exec VE return. Okay. So, what did it do? It turned into cat, right? Cat ran to completion, and then when it was done, cat got cleaned up with the operating system. So this never returned, right? When the exec VE call was successful, this went away. Your code globals heap stack, they're just gone. They're now cat, and you've turned into cat. Okay? It's a little confusing. Yeah, Jamin.
Cat is RV1?
Just by convention, that's what you put there. So when you do, so I knew someone was going to ask that question. It's a good question. Here, junk.c, we're going to call this sleep10.c. All right. So this is just going to call sleep10. I'm not going to run it because that would be boring. But now what I'll do here is I'll call sleep10. So I'm going to call sleep10. Okay. Sure, with that argv and that env. Okay. All right. You'll note, okay, so it's going to run. After 10 seconds, it'll die. Perfect. Okay. Not wait for it. Oh, no, that's right. It just turned into that process. And you'll notice, well, here, let me do this PS inside junk.c. So here, let's do system PS. I'll just do PS. It'll work. Okay. So where's my code? There it is. My in and out process is 96903. Oh, and I didn't do a PS. Dang it. All right, do that. Now here I'll do a PS that gonna work? Yeah. Okay. So there's my process, 96907, which is A.out. After I make the exec call, you'll notice it's turned into cat temp.text because that's what I set argc and argv to. And when I make the exec VE call, the operating system logs it and says, okay, there's argc and argv, so now when I do the PS listing, it's going to say what that is. So that's why the first, so the first argument is usually the name of the executable, but it can be anything you want. You notice I called it cat and the executable is sleep 10. So you can actually make it whatever you want. By convention, that's going to be the name of the process that the program that you're running. Okay? Questions on that? Okay. Now, there are a ton of execs. Try that. There we go. See if it prints it out more nicely now. There we go. There are a bunch of execs. These are all wrappers on top of exec VE. Exec VE is the one that calls everything. Exec VE is a pain to call because you usually don't care about the environment. So the other ones, if they don't have the if they don't have the environment, it automatically gets copied for you. Okay. There are two that matter. Right. The two that matter are these two: exec LP, okay, and exec VP. These are the ones that you end up calling. And in fact, in your shell, you will call exec VP. Okay. Now, what's the difference? Exec VP, all right, there are two differences between this and exec VE. First off, this is not a path but a file. So with exec VP, the P stands for path, that path environment variable. With exec VP, it's going to go ahead and find this executable in the path. So if I say cat with exec VE rather than bin cat, right? Well, it'll work, right? Whereas with exec VE, here, let's do it down here. Exec VE, if I had said cat, now exec VE is going to return because it's not going to be able to find cat. Okay, so see it returned, and the reason is because it couldn't find cat. Whereas if I call this with exec VP, now it doesn't need the environment variable, and it'll work. Okay, so it actually did do the cat command now. So that's exec VP. And then exec LP, this one's nice if you're just kind of writing, well, I don't want to say quick and dirty programs, but it is. With exec LP, what you do is you actually specify all the arguments as parameters to exec LP, and then you end it with null. So you don't have to build an argv array here. You can just put it in your program. Right, so here, let's do that too. So here we'll call exec VP, and now I can say cat. That's the program, and now I got to do the arguments. So now cat temp.text null, and that should be exec LP. Okay, so that works fine too. Okay. All right, let's click.